हेलो एवरीवन। आगे के लेक्चर में हमने कलर ट्रांसफॉर्मेशंस देखा। इन टुडेस लेक्चर वी विल सी अबाउट कलर इमेज स्मूथनिंग, शार्पनिंग, सेगमेंटेशन इन आरजीबी वेक्टर स्पेस एंड कलर एज डिटेक्शन. So now let's start with smoothing and sharpening. So color image smoothing. So grayscale image smoothing can be viewed as a special filtering operation in which the coefficients of the filtering mask have the same value. As the mask is here, as the mask is set across the image to be smooth, each pixel is replaced by the average of the pixels in a neighborhood defined by the mask. So as here, this concept is easily extended to the processing of full color images. The principal difference is that instead of scalar intensity values, we must deal with component vectors of the form given here. So let SXY denote the set of coordinates define the neighborhood centered at XY in an RGB color image. So the average of the RGB component vectors in this neighborhood is C bar of xy is equal to 1 upon k sigma st belongs to sxy into C of st. So it follows the equation and properties of the vector addition that C bar xy is equal to 1 upon k sigma st belongs to sxy, r of st, g of st and b of st. So we recognize that the components of this vector has a scalar images that would be obtained by independently smoothing each plane of the starting RGB image using conventional grayscale neighborhood processing. So consider the RGB color image here. It is red, green and blue component images which are shown here in figure B to figure D. So this figure through figure C shows the HSI components of the image. So based on the discussion in the previous paragraph, we have smoothed the each component image of the RGB image in this figure independently using 5x5 spatial averaging mask. So we then combine the individually smoothed images to form the smooth full color RGB result as here. So the result is here. So note that this image appears as we would expect from performing a spatial smoothing operation. So an important advantage of a HSI model is that it decouples intensity and color information. This makes it suitable for many grayscale processing techniques and suggests that it might be more efficient to smooth only the intensity component of HSI as represented here. So to illustrate the merits or consequences of this approach, we next smooth only the intensity component, we leaving the hue and saturation components unmodified, and convert the processed result into a RGB image for display. So the smooth color image is here. So note that it is similar to this figure, but as you can see from the difference images here, the two smooth images are not identical. This is because in this figure the color of each pixel is the average color of a pixels in the neighborhood. So on the other hand, by smoothing only the intensity component in this image, the hue and saturation of each pixel was not affected and therefore the pixel color did not change. So it follows from this observation that the difference between the two smoothing approaches would become more pronounced and a function of increasing filter size. So here now color image sharpening. So we consider image sharpening using the Laplacian from the vector analysis. We know that the Laplacian of a vector is defined vector whose components are equal to the Laplacian of the individual scalar components in the input vector. So in the RGB color system, the Laplacian of a vector C is here. Del square C of xy is equal to del square R of xy, G of xy and B of xy, which tells us we can compute the Laplacian of a full color image by computing the Laplacian of each component image separately. So this figure was obtained by this equation, and the mask in this figure to compute the Laplacians of the RGB component images. So these results were combined to produce the sharpened full color result. So this shows the similarly sharpened image based on the HSI component. So this result was generated by combining the Laplacian of intensity component with the unchanged hue and saturation components. Now image segmentation based on color. So segmentation is a process that partitioned an image into the regions. So segmentation in HSI color space. So if we wish to segment an image based on color, and in addition we want to carry out the process on individual planes, it is a natural to think first of a HSI space because color is conveniently represented in the hue image. So typically saturation is used as a masking image in order to isolate further regions of an interest in the hue image. So suppose that it is of interest or to segment that the reddish region here in the lower left of this image. So although it was generated by pseudo methods, so in this image it can be processed as a full color image without loss of generality. So this figure here figure A, B, C and D. So figure A to D, that the region in which we are interested have relatively high values of hue, indicating that the colors are on the blue magenta side of red. So figure E shows a binary mask generated by thresholding the saturation image with the threshold equal to 10% of the maximum value in the image. Here figure F is the product of the mask with the hue image, and figure G is the histogram of the product image. So the result of thresholding of the product image with threshold value 0.9 resulted in the binary image as shown in the last figure. So now segmentation in RGB vector space. Working in HSI space is more intuitive. Segmentation in one area in which results generally are obtained by using RGB color vectors. So the approach is straightforward here. Suppose that the objective is to segment objects of a specified color range in an RGB. So here given a set of sample color points representative of the colors of interest, so we obtain an estimate of the average color that we wish to segment. So let this average color be denoted by the RGB vector A. So the objective of the segmentation is to classify each RGB pixel in a given image as having color in a specified range or not. So in order to perform this comparison, it is necessary to have measure of similarity. One of the simplest measures is the Euclidean distance. So here let's Z denote an arbitrary point in the RGB space. So we can say that Z is similar to A if the distance between them is less than a specified threshold D0. So the Euclidean distance between Z and A is given by D of ZA is equal to double mod Z minus A. So the equation will be Z minus A raised to T into Z minus A whole raised to 1 by 2. So my ZR minus AR raised to square plus zg minus ag square plus zb minus ab square raised to 1 by 2. So where the subscript r, g and b denote the RGB components of a vectors a and z. So the locus point of such that z of zy is then is equal to d0 is a solid sphere of the radius d0. So the rectangular region here as shown in figure A, it contains the samples of reddish colors we wish to segment out of the color image. So this is the same problem here using hue, but here we approach the problem using RGB color vectors. So the approach followed was to compute the mean vector A using the color points contained within the rectangle in this figure. Here is the rectangle. So a box was centered at A and its dimensions along each of the RGB axes were selected as a 1.25 times the standard deviation of data along the corresponding axis. For example, let sigma r denote the standard deviation of the red components of the simple points. Then the dimensions of the box along the r axis extended from AR minus 1.25 sigma r to AR plus 1.25 sigma r, where AR is denotes the red component of the average vector A. So the result of the coding each point in the entire image as white if it was on the surface or inside the box, and the black otherwise it is shown in the figure B. So here we can see black and the white portion. So now let's see about color edge detection. So edge detection is an important tool for image segmentation. So we are interested in the issue of computing edges on an individual image basis versus computing edges directly in the color vector space. So let R, G and B is the unit vectors along the RGB axis of RGB color space and define the vectors. U is equal to sigma r upon del r upon del x r plus del g upon del x g plus del b upon del x b, as same here in the V. So let here the quantities gxx, gyy and gxy be defined in the term of the dot product. These vectors are as follows. Here gxx is equal to u into u is equal to u raised to t u is equal to mod del r upon del x square, del g upon del x square and del b upon del x square. Same as gyy, and here finally we can get here equation of g of xy. So here keep in mind that r, g and b and consequently the g's are functions of x and y. So using this notation it can be shown that the direction of maximum rate of the change of c of xy is given by the angle theta is into xy is equal to 1 by 2 tens inverse into 2gxy upon 2gxx minus gyy, and that the value of the rate change at xy in the direction of theta xy is given by f0 is equal to f0 of xy is equal to 1 upon 2 gxx plus gyy plus gxx minus gyy cos 2 theta xy plus 2gx sin theta xy raised to 1 by 2. So in this figure is the gradient of the image. So it obtained using the vector method. So this figure C shows the image obtained by the computing the gradient of each RGB component image. Here this figure shows the image here obtained by the computing the gradient of each RGB component image and it forming the composite gradient image by adding the corresponding value of the three component images at each coordinate x, y. So we have seen this figure here. So this is the corresponding values of the component. So we can say that here the edge details of the vector gradient image is more complete than the detail in the individual plane gradient image in this figure. For example, see the detail around the subject's right eye here. So the image in this figure shows the difference between the two gradient images at each point x and y, means xy. So it is important to note that both approaches yield reasonable results. Whether the extra detail in this figure shows the worth of the irrators, means which were used to generate the gradient of the individual planes. So it can only be determined by the requirements of the given problem. So we can see the difference in eyes here, and we can see the difference between this image and this image. So now this figure shows the three component gradient images which when added and were used to obtain this figure. So it is the added and scaled images of this figure. So this is the component gradient images of color image. In figure A here is a red component, figure B is a green component, and figure C is a blue component. So these three images are added and scaled to produce the image in figure C. Thank you.